Alright, now we're going to talk about operators. And continuing in the vein of applying classical terms in quantum mechanics. So, taking kinetic energy as it is classically, 1/2 mv squared, or, as you can also rewrite it, momentum squared over 2m. We want to translate this into quantum mechanics. This is how it's done. Quantum mechanically, kinetic energy is negative h bar squared over 2m second partial x. This is not a scalar anymore. This was a scalar in classical terms. This is no longer a scalar. This is now an operator, as denoted by the hat. Also, clever trick. Taking the square root of negative h bar squared will give you negative I h bar. That is awesome. It's awesome for a couple of reasons. Namely being, we can rewrite p of x like this. We can rewrite any momentum operator in any direction like this. P of y would be negative I h bar d of dy. We apply this to some function. So, for example, if that some function were to be psi of x equal to the sine 2 pi x, and let's just say we wanted to apply this term here, we wanted to apply p of x operator to psi, we would get this operation, which would yield this for the first derivative. And let's say we wanted to apply it again, we would get a second derivative. And you go through the math. It's helpful to know that I squared is 1. So helpful tips. Square root of negative h bar squared is equal to negative I h bar. And when you square I, you get 1. And if you do this math out, you get this. So that's nice. And it's important to know that if you're doing expectation value, so let's recap. We'll recap off to the side here. Expectation value of let's say x, so position, was equal to negative infinity to infinity of x px dx. Remember? And if we had, some two functions, then this would have been, running out of room, psi and psi, star, dx, with some sort of operator in here. Call it A, call it H, call it whatever. In this case, expectation values with operators, they look like this. The A hat being your operator. So before, like this. Now if you introduce an operator, it looks like this. These operators must fulfill this parameter, that the eigenfunction gives you an eigenvalue. An example would be finding the expectation value of the energy using the h hat operator. What is this, you're asking? A Hamiltonian h hat is an operator? Well, yeah, it is. Sure, look. It's just like this. If we just rewrote this, h hat operates on psi of x to yield some e eigenvalue of psi of x. This is an operator. It's operating on this guy. And if it's, well, we'll get to the commutator in just a second, but as you can see, these two do the same thing. So, getting back to our example. Try to find the expectation value of energy. You can rewrite this with the value E, or if you're given some sort of equation for E. This is possible. This translation is possible because it fulfills this condition. That's why this is possible. And it just so happens that for, I believe for 1D, I think this is one-dimensional. For one-dimensional, the expectation value E1 half plus E2 and half. This, interestingly enough, is because you can have, this is this sort of this weighted average thing going on, because you can have the energy, when you measure the energy, it will actually collapse into one or two states. So that's just sort of like the average. Right. I believe there's one more thing I need to get to. No, a couple more things I need to get to. Run on this page. The possible values from measurements must be eigenvalues of that observable operator. So that's just stating this. You know, if you go out and measure the energy of some psi wave function, this energy has to be an eigenvalue of this eigenfunction, of this observable operator. So we have a couple of observable operators. Let's say we have A hat and H hat. Both of these are able to operate on psi. If this operation yields this result, where the order of the operators switched equal each other, you know, because if you rewrite this, AHY means that this is, or psi rather, AH psi is equal to HA psi, and these have their hats. If these two are equal, then that means that they commute. Then H hat and A hat commute, and you can measure simultaneously both of these observable measurements. And you can measure these simultaneously to get an exact value. For example, the operator L sub z and H hat commute, which means you can take the L sub z operator on some state mj, or even lz on L and M, let's do that, will be equal to mh bar. Or is h bar squared? I forget now. No, just h bar. But then you can also take h bar, apply it to y of Lm, and these two operators would commute, and you would have two simultaneously exact values. So I'm gonna cut it there, but let's do a quick recap. We started off with operators, translating it from classical to quantum mechanics, applying those operators to a new scenario, and also to an old scenario with expectation values, having to fulfill this parameter that the eigenvalues of this operator eigenfunction agree, meaning you can replace them here in the integral for the expectation value. Also, we learned this thing called the commutator, which means that these two commute if this is true, and this just means that you can simultaneously measure those two observable operators and get exact values. Alright, that's time.